So they are manufacturing the control system panels, CNR panels, SAS, SCADA automations like that. So all the installation and commissioning is done by our team, and we are also having the products which are IoT based. Basically nowadays, many of the systems are IoT based, and we are continuously monitoring our substation asset also with these IoT solutions, with our transformer monitoring and feeder monitoring solutions, and also a software which is full-fledged monitoring all the substation assets which is manufactured or developed by Scope, which are our customers are using very proudly. And another sister concern of Scope is known as isosceles sales and services, and this organization is basically a um, testing and measurement uh, company which is doing the various maintenance and operation activities with the AMC contracts and all these things. So this is about the scope as an industry, and we are proud to know that we are in the market from last more than 35 plus years, and we are serving our esteemed customers up to their satisfaction. So coming to the agenda of today's topic. So today we are going to discuss about the transformer testing, basically transformer turns ratio measurement and magnetic balance testing. So we are first we'll be discussing about basics of transformer, its types, various faults and causes of transformer failures, then applicable test standard which are applicable for the transformer testing, and then we will discuss about the transformer turns ratio measurement, what is its acceptance criteria or tolerance limit. Then about the excitation current and phase angle deviation also we will discuss, and then vector group and magnetic balance test. And in the end, we will have a glance to the scope TTRM series, that is the transformer turns ratio measurement instrument supplied by the scope. And at the end, we will have a question answer session. So starting with the basics of power system. So as you all know that power system has generator or divided into three main parts. First is the generation, then transmission and distribution. So generally, in our country, in India, we are having the generation at very low voltage levels like 11 kV or 6.6 kV, 3.3 kV, and the other end, at the consumer end, we have the consumption or the users. They are using the power at 230 volt, 415 volt, or somewhat higher level at like say 3.3 kV for industrial purposes like that. But the transmission is in between the generation and the consumption, or the generation and the distribution, because as we know, the most of the power station are at the remote locations, and it is not easier to transmit the power which is generated at the remote location. If you take the example of the Maharashtra, so we are having the various power station mostly in the eastern region of the Maharashtra. We are having the super thermal power station at Chandrapur, and most of the load centers are located at the western side of the Maharashtra. You can say Mumbai, Pune, the industrial belt. Okay, so we have to transmit the power from that generated region towards the load region. Okay, so if we are going to transmit the power at same voltage level, then obviously it will be power loss, and we will get the less power at the generation or the user end. So for that, we are doing the transmission and then distribution. So in transmission, what we are doing, we are just stepping up the generated voltage at some 220 kV or 400 kV level, and then it is transmitted towards the long distance. And again, to at the end of the user end, it is we are going with the distribution segment or the distribution lines, where we are stepping down that high voltage to about 11 kV or 440 like that. So it can be very much convenient or convenience to the use of that power. Okay, so all these system is having the various substations for stepping up or stepping down the power. So transformer plays a very important role in this all this system. So we can say actually transformer is nothing but the heart of the power system. All the if you take an example of any substation, whatever may be the voltage level, the transformer is the centralized device, and all other equipments, they are there for protection of that transformer. So transformer becomes obviously the very important, and of course it is a costlier equipment in the power system. So it's our duty to being an technical engineer, it's our duty to take care of the transformer so that it can work efficiently, long life, with the less failures or with less maintenance, like that. And so that's why we are continuously going for the testing of the transformer. It can be preventive, or it can be after faults or something like that, or it can be during the manufacturing process also. So we'll see all these testings one by one. Before that, we'll see the types of the transformer. So it's a basic engineering of transformer, that transformer has various types like power transformer, distribution transformer, auto transformer, reactors, and instrument transformer. So power transformers, which we are using using for transmitting the power at long distance with the high voltages. And in the distribution transformer, we are stepping down the high voltage power to the lower voltage so that it can be very much convenient for usages. An auto transformer is nothing but the single winding transformer, which can be used as the power or distribution transformer. And the instrument transformer and nothing but the current transformer or voltage transformer. So actually, these are special type of transformer which we are using for the measurement purposes or protection purposes. So in the power system, there are high voltages and high currents are there. So it is not easier, or it is not possible actually to measure these high voltages and high current directly. So that's why we are using the CTs and PTs, that is current transformer, voltage transformer, or CVTs, that is capacitor voltage transformer. So with these transformers, we are stepping down these voltages and currents for lower voltages so that it can be safe and easier to measurement. And also these transformers, these instrument transformers, will work as a protection device also, with conjunction with the relays and circuit breakers. No, our main focus will be towards the power transformers. So main parts of the power transformers are core, winding, bushing, OLTC, main tank, and transformer oils. So transformer core is the nothing but the metallic body, and it's made up of I can say thin sheet laminations on which we are winding the transformer winding. And with the bushing, with the help of bushing, we have taken out the terminals of all the three phases of HV and LV. And with the OLTC is also an important device, or the important part of our transformer, because many of the time what happens that the voltage we are expecting at the HV side of the transformer, it not is not constant. It can be variations in the in input voltage. Okay, but if it is in the if the variations are there in input voltage, same can be happen towards the output side also, and that can be effect on the load. Whatever load we are using, it can be motor or any other resistive, or what type of load. Okay, so to avoid that, we are using OLTCs. OLTCs are nothing but the on-load tap changers. The tap changers can be on-load or off-load also. So basically, in the power transformers, we are using on-load tap changers. As per name indicates, we can operate the tap changers in the load condition also. Means transformer is in loaded condition. In that condition also, we can operate these tap changers. Okay, but in off-load, we have to shut down the transformer, and then only we can operate these offload type of transform tap changers. So in the onload tap changers, we are having the various numbers of taps: 9 taps, 17 taps, 21 taps, 5 numbers of taps. So with this tap, we can maintain the input voltage supply to the transformer so that HV's LV side or the output voltage can be made constant as per our requirement. And the Tank is the main tank of the transformer, which is having all this assembly inside it. It's some core, then your winding and OLTC, and transformer insulation, insulating oil, paper insulation. All these are assembled inside this tank. So transformer oil is also an important uh, uh, part, I can say, of the transformer, because it has to play basically two major roles. First one is the as an insulating material, and second one is the cooling medium. So this transformer oil will work as insulator and cooling material, and this main tank of the transformer, or the conservator of the tank transformer, or the radiator of the transformer, all these things, or the bushings or CTs, PTs, all these are filled with the insulating oil. Okay, so to maintain the health of this, that oil is also important thing. Okay, so for that we need to check the tan delta of that oil. We need to check the BDV, that is breakdown voltage strength of the oil. Okay, then ppm content, moisture content, uh, dissolved gas analysis. All these tests are regularly carried out on the transformer oil. So that it's basically the insulation. As long as the insulation is in any of the electrical system, any of the electrical equipment, as long as the insulation is better, your system or your equipment will work smoothly. Or whenever there is insulation failure, it will of course affect on the performance of your electrical equipment. So transformer oil is also as an important part, and to take care of that oil, it's also our major duty. Now coming towards the various faults occurred with the transformer. So first of all, we see the parameters causing the faults in the transformers. So here is the pie chart diagram. We can see here, most of the transformer failures are observed due to electrical disturbances and insulation deterioration. Okay, so means electrical disturbances means what? There can be a short circuits, there can be any other faults. Okay, there can be a thermal stresses, electrical stresses, heavy load. Okay, because of that there can be failure, and that can be at various locations. That can be at main winding, that can be at the connection between winding and bushing, that can be at your oil disease, like that. So transformer winding and core, these are the important parts, and we need to take care of that, because majority of the failures are observed there. And obviously second important thing is insulation distortion. As we said in the last slide, that as long as our insulation is better or insulation strength is good, your equipment or your system is working fine, or it working smoothly with better efficiency. But as time passes, there can be addition of impurities in the insulation, which will cause the deterioration of insulation. And because of this deterioration, the strength of the insulation will get weakened, and ultimately it will have some flowing of leakage currents. Okay, and due to that, there can be a failure of the transformer. The subsequent events can be formation of various gases. Okay, then formation of hydrocarbon gases, then formation of carbon contents, and like that. That will eventually affect to the failure of equipment, or the unwanted shutdowns, or unwanted trippings. Okay, then various parameters like inadequate maintenance, loose connections, moisture, or lightning, atmospheric lightnings. These are also the some components which are causing the transformer failures. Means inadequate maintenance means transformer should be maintained. Whenever there is a maintenance, that can be proper SOP should be followed. Okay, and if not, that can also be a cause of transformer failure. Loose connections means whenever we are connecting the transformer with the external line or something. Okay, that time there should be a proper connection. Otherwise, if the connections are loose, there will be a any type of hotspot will be there, which will eventually affect on the performance of the transformer. There will be a power loss or energy loss in the form of heat at that point. And moisture will also play an important role to deteriorate the insulation. That can be a paper insulation, or the your liquid oil insulation. So if moisture enters inside the transformer, it will affect on the performance of the insulation. And atmospheric lightning also one of the reason to the causing the fault in the transformer. Now, as we said in the last slide, the locations which are where the major faults are occurring, these are the OLTCs, tanks and bushings, windings, and some other secondary cooling or arrangements like that. So, winding or coil or the core is the more uh, major part of the transformer where we can observe the unwanted faults of the transformer. Similarly, OLTC joints or OLTC connection can also undergo the faults. And if you consider the tank, the tank is having core and insulation and paper insulation, oil insulation. So there can also be the fault can also be observed at that component or that part of the transformer also. Now, coming towards the transformer winding failure. So, main causes of transformer winding failures are the dielectric fault or the breaking or damage winding or the mechanical faults. So, means if there is a turn-to-turn insulation breakdown in the transformer, there is the tank is full of the insulating oil. Okay, and also each and every turn is having its own insulation. Between each and every turn, there is an insulation. If there is a breakdown between this insulation, then it can be cause the shorting of the turns. Okay, it will if the turns will be get shorted, then there is the change in the transformer performance parameters also, and the breakdown of the insulation results in the flashover of the winding turns. Means if there is a insulation breakdown, then turn will get short and we can observe the flashover also, and which will create the hotspot inside the transformer. And next is the damage of the winding. So thermal losses make hotspots in the winding. So if there is the breaking or damage inside the winding, it will become the turn will become open circuited, and there will be heavy resistance will occur and heat loss will be there. Okay, that can also make some hotspot inside the transformer winding. And in mechanical faults, there can be distortion, loosening, or displacement of the winding. Okay, then improper repair or bad maintenance or the corrosion or manufacturing defects can also be the cause behind the mechanical fault of the transformer. So, to avoid all these unwanted faults or unwanted trippings or failures of the transformer, as we said in the earlier, that we are regularly testing the transformer. Basically, power transformers are tested once in a year or twice in a year. Okay, so the types of tests which are conducted on the transformer that can be divided into two parts. That is which are conducted inside the factory, or other tests which are conducted on the site location in the field. Okay, so in the first box we can see the type test, routine test and special test. These tests are generally conducted inside the factory itself. So type test is nothing but in the first prototype test, whatever transformer we have designed and a prototype is manufactured, so that can be type tested first of all to prove the design and rating of the object transformer. So these tests are conducted by or the various labs or government recognized or national international labs are there. From there we have to get the certificate for this test that our transformer has passed all these tests. So these test reports are valid till there are no any design related changes inside the transformer. Okay, if you are having some design changes in the transformer, you have to again conduct this type test for this new design. Okay, and the routine test, these are the factory routine tests which are conducted on each and every individual unit. Okay, to check its performance, so that it is in line with the prototype, first prototype we are tested. So for that we are conducting the routine test inside the inside the factory during the manufacturing process or during the quality checks of the transformer. And the special tests are the customized or carried out as per the special requirement of the customer. So we are conducting the routine test during the factory inspection whenever we are having any order or we are supplying the transformer. We are conducting the routine test at the factory itself in the presence of customer. At that time, if customer asks some special test also, that can also be conducted. And now next part is the testing conducted on the field. So after all the quality checks and all these things done, the transformer is sent to the site. Okay, and in site it will be installed at the site and then commissioned. So before commissioning, we have to conduct pre-commissioning test. It is done to be at the time of commissioning, before commissioning, at the time at the site itself. Okay, so various tests which are conducted by testing engineers are the transformer winding resistance, turns ratio, magnetic balance, vector group detection, tan delta, oil testing, filtration, and all these tests are conducted on the transformer. And the periodic tests are the this purpose of routine periodic test. These are the periodic tests are yearly or 6 years, 6 monthly conducted on the field, so that to check whether the transformer is performing as per the expectation or not. And next is the emergency test. So now these emergency tests are whenever there is the failure inside the transformer, when transformer gets shut down or transformer get tripped, we have to find out the cause behind the failure. So for that, we have to conduct some tests. These are the emergency tests which are conducted on the site. Now we'll see various tests or various failure or causes of failure of the transformer and related part, and which type of test we are going to perform to diagnose this failure. Okay, so if you consider the winding of the transformer, so winding can be failure. There are types of failure like interturn short, open winding, magnetic imbalance, load loss, then mechanical damage, rise in winding temperature, partial discharge. So these can be failures observed in the transformer winding. So at the other hand, we can see various tests which we have to perform so that we can have some prediction or we can have some analysis of the whatever failure occurred with the transformer. So for example, if there is a internal short and if you conduct the transformer turns ratio, winding resistance, and excitation current test, then we can observe the incorrect results. Okay, and with the winding resistance test of all type winding resistance, that resistance versus time or current versus time test, we can observe there is some failure or some imbalance in the transformer winding. Similarly, magnetic balance test we can perform on the transformer so that to check whether if there is any magnetic imbalance or not, or if there is any mechanical damage of the winding, means we can say uh, uh, misplacement of the transformer core. Okay, or misplacement of transformer winding, or incorrect placement. In that case, we can conduct the SFRA test, and with the SFRA graph, we can compare that graph with the previous one, and from that we can identify if there is any mechanical damage inside the transformer. Similarly, if the insulation degradation of there or moisture has entered inside the transformer, then we can conduct the transformer oil DGA, partial discharge, capacitance, tan delta testing, like that. Similarly, there is another two components, that is core and bushing. So if core has some failures like core overheating or core loss or the mechanical damages inside the core, that can be also observed with the various tests like SFRA, core temperature indication, excitation current, open circuit test, like that. Now, the transformer bushing is also an important equipment which will connect your overhead line with the transformer winding. Okay, and And with the transformer bushing, we can give the minimum or required ground clearance also for the safety of the equipment. So bushing is also having its own insulation, its own oil insulation, paper insulation. If there is any type of the degradation in the insulation, then we can check with the insulation resistance or capacitance and delta. Or oil leakage, many of the time we can observe the oil leakage from the transformer bushings. Okay, the visual check or oil level indicator of the transformer or the bushing can give idea about the oil leakage inside the transformer bushing. And as we said, insulating oil is an important component or play an important role inside the transformer while its performance. So rise in oil temperature, dielectric strength, and moisture in oil, then oil quality, that can be the causes of the failure. So moisture in oil or dielectric strength, these are the main component which define the define the performance of the transformer oil. So that can be observed by conducting the oil BDV test or insulation resistance test also, or the tan delta test we can perform on the oil, so that we can observe the moisture or the dielectric strength of the oil. And Carl Fisher or Carl Fisher test or dew point test, these are the tests to observe the moisture in the oil. And the tank can be visually inspected, means we can check the drain walls, we can check the oil level indicator, we can thoroughly observe the our transformer tank, so that if there is any leakage or rusting with the transformer tank, then if there is a leakage, then your transformer oil will come out, and external air which contains the oxygen, nitrogen, or other moisture particles can enter inside the transformer. And if there is any issues in diverter switch or contact degradation of the transformer, then that can be observed by using the continuity test or winding resistance of each step or the dynamic resistance test of the transformer. Now, the possible uh, winding and core damage evaluation. To evaluate the possible winding damages, we have to perform various tests. So these are winding turns ratio, then percentage error in ratio, then phase angle deviation, excitation current vector group, and magnetic balance. So all these tests can be performed with the single transformer turns ratio measurement instrument. And with that, we can analyze the transformer winding, or we can predict if there is any abnormality or if there is any failures in the transformer winding by conducting these tests. So in the subsequent slides, we will see all these tests one by one. So first of all, transformer turns ratio measurement test, which is most widely known as the TTRM. Okay. So transformer performance depends on the specific turns or voltage ratio of the transformer. So each and every transformer has its turns ratio and voltage ratio. Okay. So what we are doing, the main purpose of the transformer is to transmit the power from one voltage level to another voltage level. Okay. So same thing we are doing here. The transformer turns ratio and voltage ratio test become more essential as it is associated with the actual performance of the or actual main functionality of the transformer. So in this test, what we are doing, we are simply applying some voltage at the HV side of the transformer, and due to transformation action, due to mutual induction, some voltage will be generated at the LV side of the transformer, and we are measuring that voltage. And calculation of these two ratio of these two voltages is nothing but our transformer voltage ratio. Similarly, we are having the transformer turns ratio measurement also. Turns ratio and voltage ratio are more about similar. We will see the relation between them in subsequent slides. So these are some IC or IEEE recommended standards where we can see in detail procedure of the transformer turns ratio measurement or the what to do, what not to do, or how to interpret the results we are observed. So all this information can be extracted out from these standards available online. Now, coming towards the transformer turns ratio measurement test. First of all, we'll see when we are going to conduct the transformer turns ratio test. So, it's a factory test. Of course, while during the transformer manufacturing process, during the quality checking, we are conducting the transformer turns ratio test at the factory itself. And installation or commissioning, we have to conduct the transformer turns ratio test during the commissioning processes before commissioning. Okay, and we are having the factory test results, and we will just compare this factory result and the site result, so that to ensure there is no any deterioration during the shipment of the transformer. Okay, and then it's a routine test or the scheduled maintenance test. Okay, so to compare the result with the factory test result and previous site test result, we will conduct this test and ensure no deterioration or there is no due to some electrical or thermal stresses, and check the healthiness of the OLTC. We are regularly conducting the test on the transformer in field. So to find out that there is the right ratio corresponding to the its rated voltage to validate design specification, we are conducting this transformer turns ratio measurement test to verify the quickly or the quality of the manufacturing processes. Means whatever manufacturing processes are followed, that can be rechecked by conducting the test on the transformer. Next, to find out that the transformer is balanced, means all three phase have the same ratios and we will get the same voltages with all three phases. To identify that, we will conduct the transformer turns ratio and magnetic balance test. This measurement is particularly important for instrument transformers also, that is CTs and PTs, because the major part of the CTs and PTs is to step down the high voltages or high current for measurement purposes, which are connected to the relays for protections also. So that's why measurement of ratio of the instrument transformer is also an important task. Now we are coming towards the tolerance limit. So recommended by the standards, the ratio should be within the limit of 0.5% of the factory test result. We have to conduct the test on the field, okay, and then we have to compare the field result with the factory test result, and it should be within 0.5% of the factory result. New, if there is a if there is a new transformer, then it can be even better, that it can be 0.1% also. And from time to time, it may be observed that the major ratio of the outer phases of three-phase transformer will be slightly different. Unless the differences are more than 0.5%, it's okay. But if the differences are increasing above 0.5%, then it's cause of worry. Okay. So we need to take the preventive actions or some remedies for the performance of that transformer. Now we are coming towards the relation between transformer turns ratio and voltage ratio. If the transformer is single phase transformer, okay, in that case, our transformer's turns ratio is always equal to the voltage ratio. Okay, so because there will not be any phase shift between the primary and secondary winding. Similarly, for the transformer, if the transformer is three phase also, in that case, if the both the winding, that is HV and LV, are in same connection, that means if the HV and LV both are in star connection or HV or LV both are in delta connection, in that case also transformer turns ratio is equal to the voltage ratio. But if the HV is in star and LV is in delta, then turns ratio is equal to voltage ratio divided by root 3. And if it is in opposite, that is LV is star and HV is delta, in that case turns ratio is equal to voltage ratio into root 3. So All these observations will be done by instrument itself, and instrument will give you the final results. Now, percentage error calculation. Now, we have observed, we have conducted the transformer turns ratio test, and we have got some results. Okay, now we have to compare that results with the factory test results, or the we can say nominal results, which are calculated values. Okay, so calculated values can be ideal. Okay, it's not important, or it's not always necessary that calculated value and measured value always match each other, but there should not be tolerance more than the limit. Okay, so percentage error will be calculated with the simple formula, that is measured ratio minus calculated ratio divided by calculated ratio into 100. We have explained it with some example. Suppose there is a transformer of 132 by 33 kV star star type of transformer, which is having 132 kV HV and LV is 33 kV. Okay, in that case, suppose the measured ratio is about 2.999 and calculated ratio is 3. In that case, ratio error will be measured ratio minus calculated divided by calculated ratio into 100, and that can be minus 0.03%. Okay, similarly, there is another example for delta star type of transformer, where measured ratio is 5.7668. Okay, and our calculated ratio, or the percentage error, we can say, is equal to 0.015%. Okay, so all these calculations, whenever we are having any type modern day transformer turns ratio measurement instruments nowadays, all these calculation will be done by the instrument itself, and it will give you the final result. Now, deviation of ratio from expected value can cause some of the failures or some of the defects in the transformer, or in other language we can say that if there is some defects in the transformer, we can observe something changes in the deviation in the ratio. If there is any manufacturing defect in the transformer, then it can be due to improper turns, or due to incorrect polarity, or incorrect winding configuration. If there is insulation failure, then we can observe damaged turn to turn insulation, or major insulation failure, that is interwinding or winding to ground insulation failure. And if the defective tap changer is there, then incorrect assembly of the winding can be observed, or high resistance or between the connection, or incorrect tap changer setting can also be observed. In that case, we can say that it's a defective tap changer. Next is excitation current test. So why we are going to conduct the excitation current test? So its need is that to analysis of the shorted turns and open turns in the winding. If there is any type of open turn or short circuit of the turns, then we will see the changes in the excitation current. So tracking the magnetic core structure, or shifting or de-shifting of the winding, that can also be observed with the excitation current test, or to check the reluctance of the magnetic circuit, increasing reluctance, which is affecting the current required to establish flux in the core. Always we have to conduct AC test or the excitation current before winding resistance test, or after demagnetization of the transformer. What happens whenever we conduct the any type of DC test on the transformer? At that time, your transformer will get magnetized. Okay, because it's a magnetic core is there. It will act as a magnet. Okay, and it will affect on the performance or the test results of the AC test, like excitation current, or magnetic balance test, or SFRA test, turns ratio test. Okay, so to avoid that, what we are doing, we are first of all conducting all the AC test, and then we are conducting the DC test. Or else after conducting any every DC test, we have to demagnetize the transformer, and then only we can energize it or we can put it in the circuit. Or else, if the transformer is magnetized and we are putting it in the circuit, it will draw a residual magnetism will draw a high inrush current initially, which will cause unwanted tripping of the transformer or unwanted functioning of the relays. Okay, so to avoid that, we should always demagnetize the transformer after every DC test, and all these AC tests should be conducted before the DC test. Now, excitation current test and analysis of test result. No, whenever we have got any results of excitation current test, how we can analyze these results or how we can put our predictions based on these results. So generally, we are getting two similar higher reading on the two outer limb edges of the transformer core and one lower reading on the center limb. That means external phases, that is R and Y, sorry, R and B. Okay, so R and B phase limb is having higher excitation current as compared to the Y phase or the central phase. Okay, and we have to compare the results with the previous one. Okay, in that case, if we can observe the 30% of the drift or the 30% difference in the excitation current of the previous result, then it's considered satisfactory. But if it is more than 30%, then we need to think of it or we need to do some remedies on that. For three-phase units, compare reading with the criteria that if the reading is below 50 milliampere, then difference should not exceed the 10%. Or the reading is above 50 milliampere, then difference should not exceed the 5%. Means if your transformer is the three-phase transformer, and generally if you are getting the excitation current value is less than 50 milliampere, then in that case the difference with the previous result should not be 10%. Or if the results we are regularly observing more than 50 milliampere, then difference should not be more than 5%. Compare results with the previous results and ensure that same voltage was used in both the tests. Means we have to keep the test condition including parameters like voltage and all should be same for both the tests. Means whatever parameters we had set for the previous test, similarly same parameters we have to set for this test also. Another thing is the phase angle deviation. So phase angle deviation is nothing but the difference between angles of HV winding and LV winding. Okay, so HV we are having the HV and LV winding in different winding configuration. Okay, it is having its some angles with respect to each other. Okay, so if that this angle is there can be a difference between these two angles. So generally this difference is very small, but if it is increasing, then there can be a damage inside the transformer core, we can say. And another test on the transformer is the polarity test. So polarity test is mostly applicable for the single phase transformers, and as we are having the vector group test on the three phase transformer, if we are using any single phase transformers parallel to our multiple transformers we are using parallel, in that case we need to check the polarity of the transformer. So it can be either 0 degree or 180 degree, that means positive or forward polarity, or the negative, that is the reverse polarity. Now next is the vector group test. Vector group is essential property for three-phase transformers. We are checking the vector group for the three-phase transformer before putting it in the parallel operation. The phase sequence of the order in which phases reach their maximum voltage and current must be identical for the parallel operation to avoid short circuit in pair of the phase in the parallel operation. So means if we are putting the any two transformers or multiple transformers in the parallel operation, then they should have the same phase sequences, same vector group, so that we will get the identical voltage, because both the transformers are going to connect with the same bus. Okay, so that the bus parameters should not get affected. That's why we need to check the vector group. And this test is important to ensure customer specified vector group of the transformer. Means this test can also be conducted, is also conducted on the field. Okay. So to identify whether the transformer is as per the required specification of the customer, we need to conduct the vector group test. Now, how we are conducting the test? So it is applicable for the three-phase transformer. An important test during the parallel operation: primary winding connected to the common voltage supply, secondary winding connected to the common load. So we can see in the picture that we are having the HV side bus and LV side bus. So HV side bus is connected with the supply and LV side bus is connected with the load. Okay. So for both the transformers in this picture, transformer A and transformer B, for both the transformers having the same voltage supply and having the same load also. Okay, so that's why it is important they are using they are working in phase, or they are working with the same vector group, or without any displacement. Now, how we are going to read the vector group? We are having some example for that. Suppose here we can see first example is yn 0. So we can see there is some method to write that vector group also. Here we can say we have written as a yn 0 with capital Y, capital N, small n, and then 0. So this bold letter or the upper class letter, capital letters indicate that it's for HV winding. Okay, so it means capital Y and capital N, it means your HV winding is in star connection and is with neutral. Okay, and similarly small y and small n, it means LV winding is also in star connection and with neutral, and the 0 indicates the phase displacement between HV and LV winding. Similarly, there is another common vector group is dy and 11, which is most widely observed in the distribution transformers. So here D is in upper class letters, that is capital letters. So D indicates delta. That means HV winding is in delta, and Y and N are in small letters. That means LV is star with neutral, and 11 is the phase displacement between HV and LV winding. Now this 11 nothing but indicating the position of the hour hand and minute hand in the clock when it is 11 o'clock of time. Okay, so it means at the time of 11 o'clock you are having the hour hand and minute hand with the 30-degree angle between them. Okay, so here 11 at the 11 o'clock minute hand is at 12 number, and 11, at 11 we are having the hour hand. That means hour hand is behind the minute hand. So it means divide 11, it means it's a 30-degree phase shift, or 30-degree lagging phase shift. Vector group detection test. So with the scope TTRM 302 instrument, we can perform the vector group detection test, and it is available in this instrument with total number of 76 vector group already incorporated in the instruments, which are widely used in the market, which contains star, delta, or zigzag type of transformers also. So these are the 76 vector groups which we are talking about, are already available with the instruments. Now the magnetic balance test. Coming towards the magnetic balance test, first of all, it's performed on three-phase transformer. It involves checking of balancing of the flux distribution. Basically, the magnetic balance test is not we can say means is not recommended by any of the standards, means IC standards or IEEE standards. No one is recommending this test, but still it is most widely conducted for checking the magnetic imbalance of the transformer, basically three-phase transformer, to identify interturn faults and magnetic imbalance due to magnetic core structure, shifting or deshifting of winding, wrong interlinked joints. We can check all these with the magnetic balance test. The voltage should be applied in one phase and it can be measured to the other two phases. So before going to this test or before starting this test, ensure that transformer is disconnected, it is de-energized and demagnetized. As we discussed some slide back, that if the transformer is magnetized, it can affect on the AC test like magnetic balance test. So you should first demagnetize the transformer and then only conduct the magnetic balance test. And we can conduct this test by keeping the transformer in the normal tap position. Now the method, what is the test method to conduct this test? So for example, we can take this transformer in the picture. Here we are having R, Y, B, three windings of the transformer wound on a transformer core. Okay, and we are applying some AC voltage at R phase. Okay, so as you can see in the picture, there will be flux generated inside the transformer core, and the flux will be flowing, or that flux will be aligned with the Y phase also and B phase also. Okay, suppose we consider the applied voltage as 100% voltage. Okay, the 100% flux will be generated inside the transformer, and the associated flux with Y and B will not be the same, because as Y phase is nearer to the R phase, more flux will be generated in Y phase comparatively B phase. Okay, so how much flux will be generated? It will be about means five. If we can say the phi 1 is the flux at R, then phi 2 will be about 60 to 90% of the phi 1, and phi 3 will be remaining 10 to 40%. And similarly, the voltage will be generated. Means suppose we are applying 100 volt to the R phase, then Y phase will have 60 to 90 volt generated voltage, and B phase will be having 10 to 40 volt. Similarly, if you apply voltage to the B phase, again you will get the higher voltage generated at Y phase and lower voltage generated at the R phase. Means it can be 60 to 90 in Y phase and 10 to 14 R phase. But if you go with the central phase, that is Y phase, if I apply 100 volt to the Y phase, then both the phases, adjacent phases, that is R and B, are at the equidistance from Y. Okay, so the flux associated with the both the phases, that is both the limbs of R and B, will be similar. Hence, we will get the voltage generated at R and B will be 50% of the whatever voltage we are applying to the Y phase. The identical results confirm no damage due to transportation. Means if we are getting these results in this fashion, as we said, 60 to 80, 60 to 90 or 10 to 40, then we can say there is no any damage. And another thing is that the whatever voltage we are observing, that can be summation of the, or whatever voltage observed is should be equal to, summation of the observed voltage should be equal to the applied voltage. Means if we are applying the voltage to B phase, then voltage generated in Y and R phase should the sum of these two voltages should be equal to the B phase voltage. So zero voltage or very negligible voltage, if it is observed, then it should be investigated. That winding should be investigated. There is some fault, we can say. So here is the table which is based on the thumb rule. We can say that if there is a star type of delta type of transformer, if we are applying the 100 volt, then we are getting the 70-30 or 50-50 voltages at other two phases. Now we coming towards the various offering or the transformer turns ratio measurement instruments offered by Scope. So Scope is offering four type of transformer turns measurement instruments. It's TTRM 302, TTRM 301, 102, and 101. So 302 and 301 are these three-phase instruments which can be directly connected to the all three phases of the three-phase transformer, and it can conduct the ratio test or magnetic balance test of all these three phases of transformer. And similarly, 102 and 101 are the single phase instruments. Okay, so 301 and 101 are the basic instruments, we can say, which can only measure the ratio, error in the ratio and polarity. But the 302 or 102 are the latest or advanced versions, which is having more specifications and parameters like along with ratio and error, excitation current, phase angle deviation, vector group, polarity, magnetic balance test can also be conducted by these two latest instruments. So we can have a glance at front fascia of our instrument, that is TTRM 302. So we can see here at the left side, we are having uh, the output part, and at the right side we are having the input part. So here we are giving the single phase AC supply to the instrument, and along with the LAN and USB connection, we can connect the instrument to the directly pen drive can also be connected with the USB, and we can copy the results. And with the LAN, we can connect to the your device like computer or laptop PCs. Okay, and inbuilt thermal printer is also provided with the emergency stop switch. In case of any of the abnormality, we can use this button or press this emergency stop to abort the test and save the instruments or the person using these instruments. And these instruments is coming with the large touchscreen display. And at the other end, at the left hand side, we are having the output. We are having the HV terminal, LV terminals, and OLTC control. So with these HV terminals, we can connect the wires or the output terminal to the HV bushings of the transformer and LV bushing of the transformer. So whenever we are conducting the transformer turns ratio measurement test, always we are applying voltage to the HV side and measuring the voltage to the LV side. It's because if you are applying the voltage to the LV side, then there can be possibility that as per transformers ratio, a high voltage will be generated at the HV side of the transformer as per transformer ratio, which is not safe to handle, or which is not easier to measure it directly. Okay, so that's why we are applying the HV voltage always to the HV side of the transformer, and at the LV side of the transformer we'll get some lower voltage, which is safe to handle, and also we can measure it directly. And the another terminal is terminal 7, that is our OLTC control. So with this, we are connecting the instrument directly to the tap changer control panel. Okay, and we can operate the tap changer right from instrument itself. Means instrument itself will send the command to the tap changer, it will operate the tap changer, and similarly it will conduct the test at each and every tap, and final results will be displayed by the instruments. So these are some test leads and other accessories which are supplied with the instruments, that is HV cable, LV cable, OLTC cable, Ethernet port, and cable for Ethernet connections, master and things, and mains cable. So these are some connections we have shown for the, we can say, conduction of the magnetic balance test on the transformer of various type of transformer. If there is a star type of transformer, then we can connect all the four windings of the HV of the instrument, to the HV side bushing of the transformer and LV winding of the instrument to the LV side bushings of the transformer. And if the one of the winding is delta, in that case, we can put the neutral in open condition and we can make the connections. In case of the auto transformer or the single phase transformer, we have to use only phase and neutral, and means one phase and neutral. So we can use the U1 phase or R phase and neutral, and other two phases are kept in open condition. And now we are coming towards the connections of the magnetic balance test. Now, how we are going to perform actually the magnetic balance test on the transformer? How we are going to connect our transformer windings or the instrument accessories or TL test lead sets? Okay, so we during the magnetic balance test, we are performing it at any one side of the transformer. Means suppose we are connecting it the HV side, if the HV side is in star connections, in that case we have to put both HV and LV winding cables to the same bushing. Means as you can see in this here first picture, that is we are having the if we are conducting the HV side magnetic balance test with the star winding, in that case HV R phase and LV R phase of the instrument will be connected, both will be connected to the R phase bushing of the HV of the transformer. Similarly, both the Y phase wires will be connected to the Y phase bushing of the HV, and both the B phase will be connected to the B phase bushing of the HV, and similarly neutral. So due to this, what will happen? We will apply the voltage from HV side of the transformer for a HV HV. We will apply the voltage to the HV side of the transformer, and then that voltage will be measured, or the if you apply voltage to the R phase, then Y phase and B phase will have some voltage generated, and then that voltage will be measured by the instrument itself, by the another windings or another wires of the our instrument connected. Similarly, we are having the pictures for star connected without neutral or delta type of winding also. And now finally, we'll have some glance at our specifications of our offered instruments, that is TTRM 302, 301, 102, and 101. Okay, so with this table, we can see all the specification of four models in a single glance. Okay, so coming to the configuration of the specification, that is 302 and 301 can test both single phase and three phase windings, while 101 and 102 can test the single phase transformers only. And all the four instruments are having the ratio range up to 20,000. Okay, means right from lower ratios to the higher ratios up to 20,000, it can measure with the better accuracy of 0.03%. And test voltages are offered from 10 volt, 40 volt, 100 volt, and at the rated frequency, rated CST frequency. And here I would like to mention that this test voltage can be customized up to 250 volt also. Means if allow if other than these three voltages, if the requirement is for 250 volt test voltage, then that can also be possible, and we can give the 250 volt test voltage also. Phase angle measurement is there, as we said earlier, in 302 and 102, and excitation current measurement up to 2000 milliampere. Now the features are there are some latest features, that is inbuilt printer, touchscreen display, then in internal storage of about 5,000 test results we can store inside the instrument itself. And with the Ethernet connection, we can connect laptop and PCs directly, and with the USB port, you can directly connect the pen drive. Suppose you are testing the transformer in the field, and we have some result. In that case, you can just directly connect the pen drive to the instrument, copy the results to the pen drive, and coming back to the office, you can sit in your office and analyze all these results. We can get the converted results in the PDF formats, and all these things can be done. Features include, as we said earlier, so all these features are listed here out, containing the automatic operation of OLTC. Means instrument itself can operate the OLTC. No need to operate the OLTC manually. Means whenever we are conducting the test for the transformers, which are having maximum numbers of taps, like 21 taps, 17 taps. At that time, it is not easier to operate transformer for each and every tap test. Okay, so for that, if you make the setting for the transformer in this instrument, then instrument itself will conduct the test, and the facility to configure the transformer ID details is possible. Means if you can create a transformer ID, okay, then in future, if you are conducting any type of test, okay, on the same transformer, then all these tests can be saved or stored under this ID only. Okay, so that it will be easier for us to compare the results in future. Inbuilt results of about 10,000 results we can store. It's a lightweight and portable instrument, and housed in the IP67 molded case for the easiness of usage in the field. And this type tested as per IEC and IS standards, safety compliance, EMC compliance, emission test, environmental test, storage test. All these tests are passed with our instrument. Now coming towards the user interface of the instrument. So it is having the various options like setting, test, record, and special functions and help option. So with the setting, we can provide the some settings like ID creation, ID selections, like that. And in test option, we are having auto test, manual test, and quick test. With the auto test, instrument will automatically conduct the test of all the whatever number of tabs are there. And in the quick test, if we are want to conduct any sudden quick test without creating any ID, that can be performed by using the quick test option. So various indications on the kit are, whenever we coming towards the testing of the electrical assets, safety is more important. So for that, the instrument should, whatever instrument we are using, should give the various indications on the screen. So emergency stop, if we are you operating the emergency stop switch, you will get the indication as emergency stop operated, and first of all release it, and then only you can operate the instrument. Then for the overcurrent also, instrument will show the error message, and polarity of the transformer will be indicated by the positive or negative sign before the whatever reading we have observed for the ratio result. Next is the software interface. So along with this instrument, we are supplying the C-Trans software for TTRM operation. So the software will be same for all the four models. We have to just select the whatever model we are using, and then there is a menu bars where we can load or import the files from instrument, or load the previously saved files. Then create setting or create ID, upload ID, then or backup and restore options are also available with this software. And here on the screen, now we can see the some test report, how the test report of actually appears. Means if at the left hand side we are having the screenshot of our instrument display, and the right hand side we are having the printed out result, which with thermal paper printer we have given with the instrument itself. So that printed out result can be can look like this. Okay, so in the printed out result, we are having all the details of the transformer, whatever we have given as an input during creating the ID. All this, all the information is printed on the result along with date, time, stamping, tab position, and the phase wise ratio value and percentage error value also. And this is the test results whenever we are generating it from the software with the in the PDF form of the instrument with the we can put the company logo also along with the header options like duty information, then results with the date and time stamping. Now, so this was about the whatever instruments we are supplying, the scope make transformer turns ratio measurement instruments. And before that we have seen various tests on the transformer, including transformer turns ratio measurement, vector group test, magnetic balance test. So whenever we are conducting any type of testing on the any type of electrical equipment, there are always some standard SOPs to be followed. There are some do's and don'ts recommended by the manufacturers, by the experts that we have to follow. So while performing the test on the transformer, there are some do's and don'ts which we will see. In do's, we are having the isolate transformer from both the sides. Before testing any transformer, make sure that transformer are isolated from both the side. Okay, and also you means thoroughly observe that the system earthing is disconnected from the transformer. Ensure firm connection to the good quality AC mains power. Okay, uh, the power supply should be proper. Okay, and it should be used with the three pin socket itself for the safety of the equipment and the user. Ensure that HV test leads is connected to the HV winding and LV test lead to the LV winding of the transformer. As we said in the earlier slide, we have to apply the voltage to the HV side of the transformer and measure to the LV side of the transformer. Hence, for that we should ensure that our instrument is connected like HV winding is connected with the HV test leads and LV is connected with the LV test leads. Earth the transformer winding from both sides before making and removing the connection from the transformer. So now we are going to connect the transformer with our instrument, or our test leads are connected with the transformer bushing. Now, as the transformer is in electrical switchyard, though our transformer is isolated, but there can be possibility that adjacent feeder or adjacent bus is in energized condition, so that transformer bushing can get some induction voltage, and that can be severe voltage also. Okay, so that's why for the safety of the person who is going to connect the test leads, we should always connect the bushings to the earth while connecting or disconnecting the whatever winding or the TLS sets. Now use fuses of specific setting. Ensure that both HV and LV terminals of kit winding are connected to the same bushing for the magnetic balance test. As we see in the previous slide, whenever we are conducting the magnetic balance test, we have to connect the HV and LV terminals for of the instrument to the same bushing of the transformer. Otherwise, we will not get the proper results for magnetic balance test. And in don'ts, we have to avoid the use of instruments in rainy season or in dusty environments. Okay, and don't touch or remove any connection during operation. Never ever use the test lead set other than the supplied with the instruments. So test leads are also specially designed for the particular instruments, considering the length of the cable, property of the conductors we are using, resistance of the cable. Okay, that can be varied material to material or length to length. So that's why we should use the proper test lead sets which is supplied by the OEM with the instrument itself. And don't use any sharp edge tools to touch the screen while operation. The instrument supplied is along with the touchscreen display. So don't use any sharp edge tools we are supplying some stylus with the instrument itself. So we should use that stylus only for operating the instruments, or for operating the menu bar, or operating the display. Don't remove or touch any connection without earthing or winding of the transformer. Means, as we said in the last slide, we have to make the earthing connection before making connection, or disconnecting the wires. So make sure that whenever you are touching the bushing, make sure that it is properly earthed, and avoid excessive vibration and bumps to the instruments, so that instruments will be more safe and it will perform in proper condition. So we are ending up now. So today we have seen various properties of transformers, types of transformers, then various faults observed by the transformers, and what are the tests we are conducting on the transformers to identify these particular faults. Okay, and especially we had a thorough discussion about the transformer turns ratio measurement, vector group, magnetic balance test, phase angle deviation, and then we had some information about scope make transformer turns ratio measurement series, which can perform all these above tests, which include the turns ratio, magnetic balance, vector group, like that. And then various do's and don'ts while conducting any type of test during the our routine activities on the field. So here we are ending up, and we are now open for the question and answer session. And meanwhile, I will let you know that if in future also, if you are having any type of doubts, or any type of requirements for the this type of instruments, you can note down these mail IDs for the various purposes, and we can write us on this mail. You can write us on this mail ID, and we will try, and we will assure you that we will give the required solution to you as per your to your satisfaction. So now we are open to question and answer session. Let's have a quick view to the question and answers.
Sagar, thank you so much for the extensive detailing about the TTRM testing and also the magnet balance test and what to do and what not to do while doing this particular test. We have few questions in the chat box. Uh,
Yes.
how many voltage may applied in this test? So, okay, so that is one. And what is the percentage voltage rated?